The morning of March 7th, 1945, Iwo Jima. Staff Sergeant James Kovacs of the 833rd Aviation Engineer Battalion stood at the edge of what used to be Airfield No. 1 and tried to calculate whether his men were building a runway or a death trap. The math was unforgiving. A Boeing B-29 Superfortress, fully loaded with fuel and bombs, weighed 74 tons. The pierced steel planking beneath his boots, the same Marston mat that had served brilliantly for P-51s and medium bombers across the Pacific, was rated for £45,000 maximum. 74 tons translated to £148,000. The engineers weren't just exceeding the design limit, they were tripling it. Kovacs watched as another damaged Superfortress approached from the north, trailing smoke from its No. 3 engine, hydraulic fluid streaming behind it like a red banner. The pilot had no choice. His fuel was gone, his crew was wounded. Iwo Jima was the only runway between him and the bottom of the Pacific Ocean. The B-29's landing gear touched down at 130 miles per hour. 37 tons of aircraft weight transferred to the main wheels in an instant. The steel planking beneath those wheels buckled, twisted, and held. Barely. That evening, Kovacs and his battalion commander reviewed the damage reports from 17 emergency landings that day. 23 sections of runway showed critical deformation. 14 sections had failed completely, punching through the volcanic ash beneath. And tomorrow, 18 more crippled Superfortresses would be coming back from Japan, each one carrying wounded men and empty fuel tanks, each one betting their lives that the runway would hold. The solution seemed obvious. Double up the matting, lay 2 complete layers of pierced steel planking instead of 1, but nobody knew if it would work. The engineers who designed Marston Mat in 1941 had never imagined aircraft this heavy. The field manuals said nothing about double-layer installation, and every hour spent experimenting was an hour that crews weren't extending the runway, weren't filling craters from Japanese artillery, weren't preparing for the next wave of aircraft that would arrive whether the runway was ready or not. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The crisis at Iwo Jima was the collision point of 2 separate engineering stories that had been building toward each other since 1941. The first was the story of how the United States learned to build airfields fast enough to keep pace with offensive operations across 6,000 miles of Pacific Ocean. The second was the story of how American bombers grew so large and heavy that the infrastructure designed to support them became obsolete before it was even fully deployed. Understanding why combat engineers started laying double Marston Mat requires understanding both stories and the terrible pressure that forced them together on a volcanic island that nobody had wanted to invade in the first place. The fundamental problem of Pacific airfield construction revealed itself in the Solomon Islands campaign of 1942. American forces captured Guadalcanal in August. They desperately needed to base fighters and medium bombers there to support further operations. Traditional airfield construction methods required months. Survey the site, clear vegetation, grade and level earth, compact the subgrade, import tons of crushed stone for the base course, pour concrete runways or lay asphalt. The Japanese had spent years building the airfield at Guadalcanal before American Marines took it. Building a new field from scratch under combat conditions seemed impossible. The solution arrived in the form of pierced steel planking, a revolutionary runway, material developed by Carnegie Illinois Steel Corporation under contract to the Army Corps of Engineers. The system used interlocking steel panels, each 10 feet long and 15 inches wide, weighing approximately 70 pounds. The panels featured hundreds of precisely stamped perforations that reduced weight while maintaining strength and interlocking hooks on the edges that allowed panels to connect without welding or bolts. A crew of trained engineers could install 1,000 square feet of runway per hour. Compare that to concrete construction, which required days just to pour and cure a similar area. The material was named Marston Mat after the town of Marston, North Carolina, where it was first tested at the Army's Airfield Construction School. The official designation was pierced steel planking, or PSP, but combat engineers universally called it Marston Mat, and the name stuck. The first combat deployment came at Guadalcanal in late 1942. Aviation engineers laid Marston Mat over the existing Japanese runway to repair bomb damage and extend the usable length. The results exceeded expectations. P-38 fighters and SBD dive bombers operated from the matting without problems. The surface drained quickly after tropical rainstorms. Damage from bombing or artillery could be repaired in hours by replacing individual panels rather than waiting for concrete to cure. The success at Guadalcanal led to doctrine that shaped the entire Pacific island hopping campaign. Instead of spending months building permanent bases, engineers would lay Marston Mat and have operational airfields within days of securing a beachhead. This allowed American air power to leapfrog forward, establishing bases that supported the next amphibious assault, which established more bases, pushing Japanese forces back across the Pacific at a pace they couldn't counter. By 1944, the pattern was refined to brutal efficiency. Marines and Army infantry would seize an island. Combat engineers would arrive in the second or third wave, equipment and materials already loaded on specialized landing ships. Within 72 hours, a functioning airfield would exist where there had been jungle or coral or volcanic rock. The statistics from Saipan in June 1944 illustrate the system at peak performance. American forces invaded on June 15th. The 804th Aviation Engineer Battalion began runway construction on June 17th, while Japanese forces still held the northern half of the island. By June 21st, P-47 fighters were operating from a 3,000-foot Marston Mat runway. By June 28th, the runway had been extended to 5,000 feet, supporting medium bombers. Total time from invasion to operational bomber base, 13 days. Traditional construction methods would have required 6 months, but the aircraft using those runways in 1942 and 1943 were fundamentally different from what was coming in 1945. A P-38 Lightning fighter weighed 17,500 pounds fully loaded. An SBD Dauntless dive bomber, 10,000 pounds. A B-25 Mitchell medium bomber, 35,000 pounds. Marston Mat had been designed and tested for aircraft in this weight range. The load calculations assumed maximum aircraft weight of 45,000 pounds with safety margins built into the design. That margin proved adequate for everything the Army Air Force operated in the early Pacific campaigns. Then the B-29 Superfortress entered service. The Boeing B-29 represented a quantum leap in aircraft design. It was conceived in 1939 as a very long-range strategic bomber, capable of striking targets thousands of miles from its base. The specifications demanded by the Army Air Corps were extraordinary for the time. 10,000-pound bomb load, range of 5,000 miles, pressurized cabin for high-altitude flight, defensive armament of 1050 caliber machine guns in remote-controlled turrets, top speed exceeding 350 miles per hour. Meeting those specifications required an aircraft of unprecedented size and weight. The B-29's wingspan measured 141 feet. The fuselage stretched 99 feet. The 4 Wright R-3350 engines, each producing 2,200 horsepower, were the most powerful aircraft engines in production. And the loaded weight, that was the number that made engineers nervous. Maximum takeoff weight was 140,000 pounds, 70 tons. Combat loaded weight with fuel and bombs pushed to 135,000 pounds. No American airfield infrastructure had been designed for aircraft this heavy. The runways at established bases in the continental United States were adequate, built with thick concrete and proper engineering. But forward bases in the Pacific, the island airfields that would actually support B-29 operations against Japan, were built with Marston Mat over whatever subgrade could be hastily prepared. Nobody knew if the matting could handle superfortresses. Nobody had tested it. The aircraft didn't exist when the runways were designed. The 21st Bomber Command began deploying B-29s to the Mariana Islands in October 1944. The Marianas, Saipan, Tinian, and Guam had been captured specifically to base superfortresses within range of Japan. The distances were staggering. 1,500 miles from the Marianas to Tokyo, 3,000 miles round trip. The B-29s would fly these missions regularly, taking off with maximum fuel and bomb loads, returning 12 to 14 hours later, frequently damaged, sometimes with wounded crews, always low on fuel. The runways on Saipan and Tinian were massive engineering projects. Northfield on Tinian eventually featured 4 parallel runways, each 8,000 feet long and 200 feet wide. The main runways were paved with asphalt over coral aggregate base, but taxiways, hard stands, and auxiliary surfaces used Marston Mat because there simply wasn't time or material to pave everything. Engineers calculated that Superfortresses operating from paved runways could use Marston Mat taxiways if the aircraft moved slowly and weight was distributed across all wheels. The calculations were theoretical. They assumed careful operation and optimal conditions. Combat operations are never optimal. The first problems appeared in November 1944. A B-29 returning from a mission to Tokyo with battle damage landed hard on Saipan's auxiliary runway. The impact load exceeded design limits. Panels buckled. The aircraft's nose wheel punched through the matting into the coral base beneath. The plane was damaged but repairable. The runway required 8 hours of work to replace failed sections and reinforce the surrounding area. Mission planners noted the incident and adjusted procedures. Damaged aircraft would land on paved runways when possible. Marston Mat surfaces were designated for taxiing and emergency use only. But the Pacific War was approaching its crescendo, and Iwo Jima was about to change every calculation about what was possible and what was necessary. The Japanese island of Iwo Jima sits 760 miles south of Tokyo. It's a miserable piece of volcanic rock, 8 square miles of black sand, sulfur deposits, and steep terrain. Nobody wanted it for its own sake. Strategically, though, Iwo Jima was invaluable. Japanese fighters based there intercepted B-29s flying from the Marianas to Japan. Japanese radar stations provided early warning of American bombing raids. And most critically, Iwo Jima sat almost exactly halfway between the Marianas and Tokyo. American planners recognized what that distance meant. A B-29 damaged over Japan, struggling to stay, airborne with failing engines or wounded crew, could potentially reach Iwo Jima. If American forces controlled it, if the airfields there could support superfortresses, if the infrastructure existed to refuel and repair aircraft. 760 miles was marginal range for a crippled bomber, but it was possible. Without Iwo Jima, damaged B-29s had 2 choices: ditch in the Pacific Ocean and hope for rescue, or attempt the 1,500-mile flight back to the Marianas with failing systems and empty fuel tanks. Most didn't make it. The decision to invade Iwo Jima was driven primarily by this calculation. Capturing the island would save hundreds of American aircrews. It would allow fighter escorts to accompany bombers all the way to Japan and back, something impossible when fighters had to fly from the Marianas. And it would deprive Japan of a forward radar and interception base. The cost would be horrific. Japanese forces had fortified Iwo Jima extensively, with tunnels, bunkers, and artillery positions built into the volcanic rock, but the potential to save bomber crews justified the casualties of invasion. The Marines landed on February 19, 1945. Airfield No. 1, on the southern end of the island, was the immediate objective. Japanese forces had built it, a single runway approximately 4,000 feet long. American intelligence knew the Japanese had been extending the runway and improving it for their own bomber operations. If the Marines could capture it intact, engineers could have an operational field within days. The landing was brutal. Japanese artillery and mortars pounded the beaches. Marines pushed inland yard by yard through volcanic sand that gave no cover and made movement exhausting. But by February 23rd, the southern portion of Airfield No. 1 was secure enough for engineers to begin work. The 831st and 833rd Aviation Engineer Battalions arrived with their equipment on February 25th. What they found was not encouraging. The Japanese runway was heavily cratered by naval bombardment and airstrikes. Unexploded ordnance littered the area. Japanese positions on Mount Suribachi, still under marine assault, had direct observation and could call artillery onto the runway. And the runway itself was built on volcanic ash and black sand, the worst possible subgrade for airfield construction. Ash provided no load-bearing capacity. It couldn't be compacted. Heavy weight simply pressed through it. Despite these conditions, engineers went to work immediately. The urgency was absolute. Every day without an operational runway meant more B-29s would ditch in the ocean. Crews filled craters with whatever material was available, crushed coral shipped from other islands, volcanic rock blasted from nearby outcrops, compacted ash mixed with soil stabilizers. They bulldozed the surrounding area flat, removing Japanese fortifications and debris. They began laying Marston mat over the prepared surface. And on March 4th, just 9 days after engineers arrived, a C-46 transport landed to deliver medical supplies and evacuate wounded Marines. The runway was operational, technically. Then, on March 4th, a crippled B-29 appeared. The Dynamite, a superfortress from the 20th Air Force, had been shot up over Tokyo. One engine was dead, another was failing. Hydraulic systems were damaged. The pilot radioed Iwo Jima control. He was coming in whether the runway could handle it or not. There was nowhere else to go. The Dynamite touched down at 135 miles per hour. Main landing gear struck the Marston Mat runway. The panels flexed, deformed visibly, but held. The bomber rolled to a stop. The crew climbed out, kissed the volcanic ash, and thanked the engineers who'd built the runway they'd just landed on. It was the first of thousands of emergency landings that would occur at Iwo Jima. It was also the moment engineers realized their calculations had been optimistic. Staff Sergeant Kovac and his crew examined the runway after the Dynamite landed. The damage was obvious. 22 panels showed permanent deformation, bent beyond their elastic limit. 8 panels had failed completely at the interlocking seams, pulling apart under stress. The volcanic ash beneath had compressed, creating shallow depressions. The total damaged area covered approximately 200 feet of runway. They repaired it that night, pulling damaged panels and installing replacements, adding crushed coral fill beneath to improve the subgrade, reinforcing the seams with additional connecting clips. The repairs took 6 hours and consumed materials that had been allocated for runway extension. The next day, 3 more B-29s made emergency landings. More panels failed, more ash compressed. More time and material went into repairs rather than construction. By March 7th, 17 B-29s had used the runway, and the engineers faced an inescapable conclusion. Single-layer Marston mat over volcanic ash could not reliably support B-29 operations. The matting would hold for a few landings, perhaps a dozen, before accumulated damage required complete replacement. That wasn't sustainable. B-29 missions over Japan were generating multiple damaged aircraft every day. Intelligence estimates predicted the number would increase as bombing intensity increased. Iwo Jima needed a runway that could handle hundreds of superfortress landings, not dozens. The engineers had 4 options, all of them bad. First option: halt B-29 landings until a proper paved runway could be constructed. Impossible. Aircraft were already inbound. Crews would die if Iwo Jima turned them away. Second option: continue with single-layer matting and accept constant repair cycles. Unacceptable. The damage was accumulating faster than repairs, could keep pace. Third option: excavate the volcanic ash and replace it with proper base material, then install matting over the improved subgrade. Theoretically sound, but would require weeks and massive quantities of imported material. Hundreds of B-29s would arrive during those weeks. Fourth option: double up the matting. Install 2 complete layers of Marston mat, one on top of the other, distributing load across more steel and more surface area. Nobody knew if it would work. It wasn't in any manual. The steel panels weren't designed to interlock across multiple layers, but it was the only option that might provide immediate improvement without halting operations. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Lieutenant Colonel Edward Peck, commanding officer of the 833rd Aviation Engineer Battalion, made the decision on March 8th. His written order was characteristically terse. Effective immediately, install double-layer PSP on primary runway surfaces. Test section first. Expand if successful. Maintain operations. Kovach's platoon drew the test assignment. They selected a 300-foot section of runway that had failed twice already, a known problem area where volcanic ash provided minimal support. The installation procedure had to be developed from scratch. Standard Marston mat installation. Standard Marston mat installation involved laying panels in a staggered pattern, like bricks in a wall, with each panel hooking into its neighbours through interlocking edges. The panels were designed to be installed directly on prepared ground, not on top of other panels. Installing a second layer meant the lower layer's perforations would provide minimal load distribution. The upper layer would essentially float on the peaks and valleys of the lower layer's corrugated surface. Kovach's crew began the test installation at dawn on March 9th. They laid the first layer using standard procedures, orienting panels perpendicular to the runway centerline for maximum strength across the direction of aircraft travel. Each panel was connected to its neighbours, creating a continuous steel mat. Then came the experimental part. The second layer was installed at 90 degrees to the first, running parallel to the runway rather than across it. This cross-pattern orientation meant stress from aircraft wheels would be distributed through both layers in different directions, theoretically preventing the concentrated load failure that had plagued single-layer sections. The interlocking hooks on the upper layer panels didn't engage with anything solid, they simply rested on the perforated surface of the lower layer. Engineers used additional steel connecting clips, hundreds of them, to link upper and lower layers at regular intervals. The clips weren't part of the original Marston mat system. They were improvised from whatever steel stock was available, bent and cut to hook through perforations in both layers. It was crude field engineering, but it created mechanical connection between layers. The test section was completed by March 10th. Total weight of steel increased from approximately 40,000 pounds per 300 feet of single-layer runway to 80,000 pounds for the double layer. Material consumption doubled, which meant runway extension would slow. But if it worked, if the double layer could handle repeated Superfortress landings without failure, the trade-off would be worth it. The test came that afternoon. A B-29 from the 313th Bombardment Wing, battle-damaged over Osaka, diverted to Iwo Jima with 2 engines out and the third running rough. The pilot requested the smoothest section of runway available. Ground control directed him to Kovach's test section without explaining it was an experiment. The Superfortress came in fast, 140 miles per hour, heavier than normal because damaged fuel transfer systems prevented burning down the aft tanks. Touchdown weight was approximately 76 tons, the highest yet recorded at Iwo Jima. Main gear struck the double-layer matting. The steel flexed, absorbing the impact through both layers. Panels deformed slightly but didn't fail. The Boeing rolled 3,000 feet and stopped. Kovach and his crew sprinted to the touchdown zone as soon as the aircraft cleared. They examined every panel where the main wheels had struck. Surface deformation was minimal. The upper layer showed slight bending, where wheels had concentrated load, but nothing approaching failure. The lower layer, protected by the upper layer, showed almost no additional stress beyond what it had accumulated during previous landings. Most importantly, the volcanic ash beneath had not compressed further. The double layer was distributing weight across enough surface area that ground pressure remained below the ash's bearing capacity. Lieutenant Colonel Peck ordered immediate expansion. Every primary runway surface would receive double-layer treatment. Taxiways and secondary areas would remain single-layer to conserve material, but anywhere a Superfortress might land at high speed with full weight would get the double mat. The work began immediately and continued around the clock. Engineers worked in shifts, installing panels under floodlights when darkness fell, pausing only when Japanese artillery fire forced them into shelters, resuming as soon as the barrage lifted. The logistics were staggering. A double-layer runway, 8,000 feet long and 200 feet wide, required approximately 21,000 panels. Each panel weighed 70 pounds. Total steel weight exceeded 700 tons. All of it had to be shipped from Guam or Hawaii aboard specialized landing ships, offloaded on Iwo Jima's volcanic beaches using amphibious vehicles and cranes, transported inland to the airfield on trucks that struggled through the ash, and installed by hand by engineers working in a combat zone where Japanese holdouts still conducted nighttime infiltration attacks. Material arrived in convoys throughout March. Liberty ships and LSTs, landing ships tank, delivered crated panels stacked in their holds. Cranes lifted the crates onto waiting trucks. The trucks formed convoys that rumbled up the beach road to Airfield No. 1, unloaded their cargo beside the runway, and returned for more. Aviation engineers worked alongside marine engineers and Navy Seabees, all focused on the single mission of getting the runway operational for sustained heavy bomber operations. By March 15th, half of Airfield No. 1's primary runway featured double-layer matting. The difference was measurable. Runway failure rates dropped from approximately 3 failures per 10 landings to less than 1 failure per 50 landings. Maintenance time decreased. Material consumption for repairs decreased. And most critically, B-29 crews gained confidence that Iwo Jima could handle them. Pilots who had been nursing damaged aircraft past Iwo Jima, attempting to reach the Marianas rather than risk a runway collapse, now diverted immediately when they had problems. The human cost of building that runway is often forgotten in technical discussions of Marston, Matt, and load calculations. The 831st and 833rd Aviation Engineer Battalions suffered casualties throughout March. Japanese artillery on the northern part of the island, still contested by Marines, had observed positions overlooking the airfield. Mortars and artillery shells fell randomly on engineers working in the open. 15 engineers were killed by artillery fire during runway construction. 42 were wounded seriously enough to require evacuation. Others died from accidents, equipment failures, vehicles rolling over in the treacherous volcanic ash. Private First Class Daniel Reyes of the 833rd wrote home on March 18th, describing conditions in letters that his family preserved. "We work 20-hour days," he wrote, 4 hours on, 1 hour off, back to work. The Japs shell us at irregular times, so you can't predict when it's safe. You just keep working and hope. Yesterday, a B-29 came in trailing fire from its wing. It landed on the section we'd finished that morning, rolled to a stop. 11 men climbed out. They were crying, some of them. Crying because they didn't think they'd make it, and then they did. That's why we're here. That's why it's worth it. The engineering achievement was matched by the operational results. By April 1945, Iwo Jima had handled over 800 emergency B-29 landings. The number would eventually exceed 2,400 before the war ended. Each landing represented an aircraft that would otherwise have ditched in the Pacific or crashed attempting to reach the Marianas. Each landing represented 11 men saved, an entire bomber crew that went home instead of dying in the ocean. The double Marston Matt technique developed at Iwo Jima became standard procedure for heavy bomber operations. Engineers deployed the method at Okinawa when that island was captured in April 1945. They used it at airfields in the Philippines, being upgraded for B-29 operations. They documented it in field manuals with detailed installation procedures, material requirements, and load calculations. What had been an improvised field solution became official doctrine. The underlying engineering principle was elegant in its simplicity. Pierced steel planking derived its strength from thin steel panels, formed into corrugated shapes that resisted bending. A single layer could handle moderate loads, but failed when concentrated weight exceeded the steel's elastic limit. 2 layers, oriented perpendicular to each other, created a grid structure where load distributed through both layers simultaneously. The upper layer spread weight across multiple lower layer panels. The lower layer transferred that distributed weight to the subgrade across a much wider area. Total load-bearing capacity didn't simply double. It increased by a factor of approximately 3 because the cross-pattern orientation prevented stress concentration. German and Japanese engineers, examining American Pacific airfields after the war, expressed astonishment at the double-layer matting. German airfield construction doctrine relied on thick concrete runways, permanent installations that required months to build and were vulnerable to bombing. Japanese doctrine used compacted coral or earth runways that required constant maintenance and couldn't support heavy aircraft during monsoon seasons. Neither had developed anything comparable to pierced steel planking, and the double-layer technique was beyond their engineering framework entirely. A captured Japanese engineering manual from Okinawa, translated by American intelligence, included observations on American airfield construction methods. The translation was stilted, but the meaning clear. Enemy demonstrates ability to construct operational airfields on unsuitable terrain in impossibly short time periods. Runway surfaces withstand aircraft weights that would destroy our runways. Method of construction unknown. Appears to use prefabricated steel matting in multiple layers. Recommend immediate research into similar techniques. The research never happened. Japan lacked the industrial capacity to manufacture pierced steel planking at scale by 1945. Even if they'd had the capacity, they lacked the transport shipping to deliver thousands of tons of steel panels to remote islands. And they lacked the time. American air power, operating from those Marston Matting runways, was systematically destroying Japanese infrastructure faster than it could be rebuilt. The broader story of Marston Matting in the Pacific War is a case study in how infrastructure enables operational capability. The pierced steel planking system allowed the United States to project air power across distances that conventional airfield construction couldn't have supported. Island bases that would have required 6 months to build with concrete were operational in weeks with matting. Air campaigns that would have been impossible due to range limitations became routine when intermediate airfields could be established rapidly. The material statistics are staggering. Between 1942 and 1945, American industry produced over 2 million tons of pierced steel planking. That steel went to airfields in the Pacific, Europe, North Africa, India, China, and Alaska. It covered runways, taxiways, roads, hardstands, and even temporary bridges. The steel came from mills in Pennsylvania, Ohio, and Illinois, was formed into panels at fabrication plants across the industrial Midwest, shipped to ports on both coasts, loaded aboard Liberty ships and cargo vessels, transported thousands of miles to combat zones, and installed by combat engineers under fire. The human element of that supply chain is often overlooked. Steel workers who produced the raw material, factory workers who stamped and formed panels, longshoremen who loaded ships, merchant mariners who transported material across submarine-infested oceans, navy crews who escorted convoys, and finally, the combat engineers who unloaded the steel on hostile beaches and installed it while being shot at. Each B-29 that landed safely at Iwo Jima represented not just the 11 men in that crew, but the thousands of people whose work had built the runway beneath their wheels. Technical innovation in warfare often focuses on weapon systems, fighters, bombers, tanks, artillery. The infrastructure that enables those weapons to function receives less attention but is equally critical. Marston Matting wasn't glamorous. It didn't shoot down enemy aircraft or sink ships, but it multiplied the effectiveness of every aircraft that operated from it by enabling operations that would otherwise have been impossible. The double-layer technique developed at Iwo Jima multiplied that multiplication, extending capability to aircraft that exceeded original design specifications. Clinton Hanna's gun stabilizer for Sherman tanks and the double Marston Matting technique share a common thread. Both were engineering solutions to problems that doctrine said were impossible. Both were initially rejected or ignored by users who didn't trust unfamiliar technology. Both proved their worth under the absolute pressure of combat where failure meant death. And both became standard practice. Once combat results demonstrated their value beyond theoretical argument. The legacy extends beyond World War II. Modern military airfield construction still uses matting systems descended from Marston Matting. The materials have evolved. Aluminum replaced steel for weight savings. Modern composite materials offer better strength-to-weight ratios. But the fundamental principle remains identical: prefabricated interlocking panels that can be rapidly deployed to create operational runways on unprepared surfaces. AM2 matting, the standard system used by American forces from Vietnam through the Gulf War, traces its direct lineage to 1941 Marston Mat. Current systems like the deployable rapid assembly shelter and Airfield Mat-2 still use the same basic cross-pattern double-layer technique developed on Iwo Jima. The volcanic island itself is quiet now. Iwo Jima was returned to Japanese control in 1968. The airfield, built with so much American blood and steel, is maintained by the Japanese self-defense forces. Commercial aircraft don't land there. It's too remote, too small, too historically painful for regular use. But the runways remain. Sections of original Marston Mat still visible beneath newer pavement, a physical reminder of what combat engineers accomplished in the spring of 1945. Veterans of the aviation engineer battalions rarely spoke about their work with the drama that combat veterans described battles. Their contributions didn't involve direct combat against enemy soldiers. They fought against terrain, weather, material limitations, and time. Staff Sergeant James Kovacs, who supervised the first double-layer test section, was interviewed for an oral history project in 1987. His description was characteristically modest. "We just did what needed doing," he said. "The B-29s were coming whether we were ready or not. Men's lives depended on that runway holding up, so we figured out how to make it hold. It wasn't complicated engineering, just common sense and a lot of steel. The hard part was doing it fast enough and under fire. But you don't think about that when you're working. You think about the next plane that's going to land and whether the runway will be ready." The final statistics tell the story that individual experiences can't fully capture. Iwo Jima's airfields handled 2,461 emergency B-29 landings between March 1945 and August 1945. Each landing saved an average crew of 11 men. Total aircrew saved, approximately 27,000. Add navigators, bombardiers, engineers, gunners, men who would have died in the Pacific Ocean without that runway. The number exceeds the total casualties of the Marine Corps units that captured Iwo Jima in the first place, approximately 26,000 killed and wounded. The engineers built the runways that justified the invasion. They did it with steel panels, volcanic ash, improvised techniques, and extraordinary determination. They did it while being shelled. They did it while watching B-29s crash on runways that failed, killing crews they couldn't save. They did it because the alternative was unacceptable, letting men die when engineering solutions existed. The double Marston Mat technique was never officially named. It didn't receive a designation or appear in technical manuals as a formal system. Engineers simply called it double mat or double layer PSP. The bureaucratic military system, obsessed with designations and official nomenclature, never caught up with field innovation. By the time headquarters staff would have standardized the terminology, the war was over, and the technique was already established practice that needed no official blessing. That absence of formal recognition is perhaps fitting. Combat engineers rarely received recognition proportional to their contributions. Aviation engineers at Iwo Jima received unit citations and individual decorations for valor, but their work was overshadowed by the dramatic Marine Corps battle for the island and the strategic bombing campaign those runways enabled. The engineers were infrastructure, invisible when functioning correctly, noticed only when they failed. But the 27,000 aircrew members who landed safely at Iwo Jima knew. They understood exactly what those runways meant. B-29 crews developed a ritual. When they made emergency landings at Iwo Jima, after they'd shut down engines and climbed out of their aircraft, they would find the nearest engineer and shake his hand. Often they'd just say thank you. So the 70 Often they'd just say, "Thank you." The engineers would nod, acknowledge the thanks, and there were always more panels to install, more sections to repair, more aircraft inbound that would need a runway that held. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.